Alright, today's video is on properties of logarithms, and we have 7 properties in total. So what I want your goal for today to be is that you can identify the properties of a logarithmic function. I want you to be able to apply them, and even some of them I want you to be able to explain. And you'll see that it's not outside the realm of reason, because the 7 properties that we're going to have today, so I'm just going to show you in general. So here we're going to talk about them each specifically. The 7 properties, what are we going to use them for? Well, it allows us to simplify when solving equations. Okay. And then, of course, there are the applications for logarithms. Now, the applications we deal with aren't quite going to use the properties extensively, but for anyone that's going into study on sound and you're dealing with decibels, okay, you're going to deal with logarithmic applications. For those that took chemistry, you have pH scale. For those that are going into maybe fields of geology, you have Richter scale. So the list goes on and on as to the applications for the logarithms, and the properties are so important because a lot of the applications stem from those 7 properties. So we're going way back to scratch here, the ground one, because this is the first time you've seen the logarithms. So I've got, this page has got the wrong number. It should only be 3 very basic properties here. And the 3 basic properties are simply this. The first one is log of any base of 1 is always equal to 0. Okay, so it doesn't matter what the base is, log base 10 of 1, log base 20 of 1, it's always equal to 0. And just a quick proof, why is that? Well, if we take log base a of 1 equals 0, and we rewrite it into exponential form, so we write it as its inverse, we find that a to the exponent 0 is equal to 1. All right, so there's the proof in itself, okay, that anything to the exponent 0 is always 1, so therefore that property is related to the property that we talked about when we did our review of basic exponential functions from grade 9. The second one, log base a, of a to the x is equal to x. So if the base of the log and the base for the exponential expression match up, so these 2 bases, if they're the same, then this is just equal to the exponent itself. Okay, so it's another one you want to add to your formula sheet. And let's talk about the y here. So proof. Most of these proofs, I like them because they're just simply rewriting them in exponential notation. It takes care of the proof. So if we take that expression, log base a of a to the x, rewrite it in, oops, I forgot my equals x, write it in exponential form, so we just write it as the inverse. The argument comes out front, okay, so a to the x would equal the base to the term on the other side. Okay, so just to help you out here, this, oops, what I'm going to highlight in yellow here, that became our term here. And then the other 2 terms, which I don't know if green will work, these 2 guys, when we put it together, form the right side. So again, it looks like common sense, but a to the x equals a to the x. So that's why when you have 2 bases the same, it's just the value of the exponent. And the third and final term, if we have a to the exponent log a of x, so the logarithm appears up in the exponent, this is just equal to x. And again, the reason for that is because, by definition, this is the inverse of each other. So it's really undoing each other. And I can show it up as a proof. So the proof here, if we rewrite this as a logarithm, because right now it's an exponential, so if I rewrite this as a logarithm, we find that the base remains the same, and the exponent is what this is going to be equal to, equals log of the base, which was a, and of the value on the other side. So just to help you kind of follow along where everything went, the exponent, that's what that's equal to, and the base and that term is what goes into the logarithm. So again, it's common sense because it's the exact same thing, but it's an inverse operation. So really, when you have base a to the exponent log a, it's undoing each other. It's like saying the square root of a square. Okay, so just as a think of it this way, if I ask you what's the square root of 3 squared, well, you know that that's the square root of 9, which is the square root of 3. So essentially, this exponent cancels out this radical sign, so you're just left with the 3. Okay? Same thing up above here. That a to the exponent log a, they essentially cancel each other out, and you're only left with x. So those are the first 3 basic terms, or sorry, basic properties. You want to make sure that you do have those on that cheat sheet, because it's going to be important in the sense that it is going to come up from time to time. Okay, advanced properties. With the advanced properties, excuse me, allows us to do a couple of more steps. So I'm going to do maybe one proof here to show you where it comes from. I'll pick and choose anyway. So the first one is, if we have the log base b of 2 things multiplied together, it's the same as the log of base b m plus log of base b n. Okay, so this is what we call our product rule here. So if we're multiplying 2 terms inside the logarithm, we can break it apart into 1 plus the other term. Okay, it's just from our basic properties. So the general proof here. Okay, what we would do, I might end up moving the 3 down a little bit. So if we let b equal log base bm, and we let log base b of n, okay, we rewrite them in exponential notation. Okay, I'm going to have to change. I can't have the base and the value the same. So if you want to, let's change that letter. And it's the same with the other one. So let's go with A on this side, and over here we'll have C. So if we rewrite this, this will be b to the exponent a equals m. Over here we'll have b to the exponent c equals n. So I've rewritten those. Okay. So if I go back to the original statement, m multiplied by n, I'm going to replace m and n with the values they're equal to. Okay. So the m is going to get replaced with b to the exponent a. So I'm going to take the log base b of m is replaced with b to the a, multiplied by n is b to the c. Now, when we look inside the brackets here, this is our exponent laws. We would add the exponents together. So log base b of b to the exponent a plus c. And if we go back, you remember that if the bases are the same, so I'm looking at this general property right here, if the bases are the same, it's just the exponent that's your answer. So when I come back here, the bases are the same right here, so they're really canceling each other out. So the answer is just going to be a plus c, and a plus c is equal to log base b of m plus log base b of n. Okay, so that and that we've just proven to be equal. All right, so I'm not going to go through and do every proof, but they're of the same nature. Okay, so this absolutely must go on cheat sheet. The second rule is our division rule. So log of m divided by n. Very, very similar, except this time it's going to be subtraction. And I guess I've been using a different base. So base b of m minus log base b n. So that's your second one. You want to make sure that gets on there. And then I'm going to slip number 3 and 4 down below here. So for number 3, it is our power of powers. So we have log a m to the exponent n, and that's equal to n log base a of m. And this is the one, if you recall yesterday, when we were, how do you calculate change of base? Here's the property that helped us out in solving that. I just want to do that proof kind of quick so you can, so I can prove to you that it was actually true, because I promised that yesterday. I know there'll be a couple of you upset if I don't. So here's the proof, just to show you that it is true. If I set that expression equal to, oops, sorry. So I got log base a m. I'm going to set it equal to some value b, which would tell me that a to the exponent b, if I rewrite it in exponential notation, it's going to look like that. So when I go back to the original statement, m to the n, where are we here? A m to the exponent n. I'm going to replace m. I'm going to take this. I'm going to replace that m with that value. So I end up with log base a, and instead of m, I'm going to replace it with a to the exponent b, the exponent n. I'm going to use my exponent rules here. That's going to be to the exponent b times n now. We already just talked about that if you have the bases are the same here with a logarithm, they're really undoing each other. So that means that it's just going to be our exponent that this is equal to, b times n. And my n apparently went lowercase for a while. What's b equal to? If we look up above, we know that b is equal to log base log of base am. So the n is now out front, log base a of m. So this is proven to be equal to that. All right. So that's why, and we're going to use these when we're solving equations. So you need to have these three particular, or six, I should say, 6 laws identified when we go through. All right. The next video then will deal with the examples related to these concepts.